Here we take a look at the Wittig reaction. The Wittig reaction is a reaction that allows us to convert a carbonyl directly into an alkene. This reaction was first published by Wittig in 1954, and he ended up winning the 1981 Nobel Prize in Chemistry for this reaction. So in this reaction, again, we're going to start with an aldehyde or ketone. And to that, we're going to need to add an ylide. An ylide can be made from this phosphorus compound plus a strong base like butyllithium that will remove this hydrogen. And give us what's known again as an ylide. That ylide will react with our carbonyl to form an alkene. And that alkene that forms is always going to be formed between the carbon of the ylide and the carbon of the carbonyl. The phosphorus group as well as the oxygen will end up combining to form the byproduct triphenylphosphine oxide. Now there's a variety of different types of ylides that can be used for this reaction. And Wittig reactions are generally important enough to the point that you can actually buy either the precursor to the ylide, the compound that needs to be deprotonated, or in some cases, like with this compound, so this carbon right here is extremely acidic because once you form this anion, that anion can be stabilized by resonance into the phosphorus or into the carbonyl. So it turns out some ylides, and this one's a good example, ylides are so stable you can actually make them and stick them in a bottle, save them, or even just purchase them and then not have to actually make the ylide. Regardless, again, we're going to form a double bond between the carbon of the carbonyl, which is this carbon here, and the carbon of the ylide. This reaction works well for both aldehydes and ketones, and is very, very useful synthetically because a couple of different reasons. First of all, we're making a new carbon-carbon bond. And we know in synthesis that reactions that make carbon-carbon bonds are very, very useful to us. Second, not only are we making a new carbon-carbon bond, but we're making it as an alkene. So if you think about all the reactions of alkenes that you may have learned, as soon as you finish the Wittig reaction, all of the reactions of alkenes are available to you to continue to build upon this molecule. Finally, a lot of ylides, because of their ease of use and their stability, will contain these carbonyl groups attached to the carbon that's attached to the phosphorus. And so as it did in this case, it also leaves us with an ester or other types of carbonyls attached to the double bond. And so that means that now 1,4 additions to carbonyls can be available, as well as any of the nucleophilic acyl substitution reactions. So very, very powerful reaction because it helps us to build up a lot of complexity, relatively quickly in a synthesis. So how does this work mechanistically? So once we form the ylide, and this is a place where you will see a couple of different mechanisms cited in textbooks. I'm just going to go with one of them. This is the better supported mechanism. But the carbon end of the ylide is partially negatively charged, or in another resonance form is completely negatively charged. You can also draw an ylide like that. And so that end of the ylide is going to attack the carbonyl. And in a lot of the old mechanisms, you would just see this and the electrons would then go up onto oxygen. But now it's more likely a 2+2 cycloaddition. And these two steps happen simultaneously. The pi electrons from the carbon-phosphorus bond attack the carbonyl, and the carbon-oxygen's pi electrons attack the phosphorus. Again, the older mechanism for this reaction would still have gotten you to this intermediate, which is known as an oxophosphate, but it did it over two steps. So nucleophilic attack to the carbonyl, and then in a second step, the negatively charged oxygen would attack the phosphorus. Second and final step of this mechanism is that the oxophosphate undergoes a retro 2+2 cycloaddition, where this four-member ring breaks down, and we form the alkene plus triphenylphosphine oxide.